All right, bonjour, welcome back to, was it week 10, week 11, something like that? I forget what week it is. Anyways, we will talk about sockets today, which is the foundation of your web browser, internet, all networking stuff is going to use sockets. So if you ever want to use networking, you will use sockets. But luckily enough for us, sockets are just another form of IPC. There's really anything different that we haven't seen before. So, like I said, another form of IPC. If we don't remember what IPC is, that is inter-process communication, or just sending bytes between two different processes. So this is how your web server works. Even using your web browser is technically IPC. So your web browser runs as a process, or each individual tab runs as a process, and you're communicating with another process on another machine, hosted by Google, hosted by Amazon, something like that. But it's just another process running on another machine, and the other process is a web server. So we've seen pipes, we've seen signals, we've also talked about shared memory, how you can use that to share between processes. But these forms of IPC assume you are on the same physical machine. Obviously, shared memory is not going to work between machines because they don't have access to the same memory. So sockets are the first form of IPC we'll see that's between physical machines, and typically this will be over a network and using your network card, Ethernet, Wi-Fi, all that fun stuff. So it's a bit more involved to set up some communication between sockets, and typically there's a server and a client. So first we'll go over the steps for the server. So if the server wants to use a socket, there's 4 steps. They're basically system calls, all our usual C wrappers, returns -1 if there's an error, sets error no, all that fun stuff. So the first system call is called socket, and it creates a socket. And we'll see the 2 options you have for that. Basically, you only have 2 options. And then after you have a generic socket that just sets up kind of a protocol, well, this next step you have to do is step 2, bind, and that is giving a name to the socket, attaching it to some location. So you can bind the socket to a file, so it looks like a file you can access, mostly if you're just testing, because that would have to be on the same machine. Or it could be like an IP and a port, which is what you're more used to if you've used anything online. Then the next step you want to do if you are a server is that listen system call that indicates you're accepting connections and will create a queue internally in the kernel for any incoming connections to be held and handled, and you pretty much just always use the default value for that, but it's just another step you have to go through because the queue is managed by the kernel, so you have to tell it how big the queue needs to be. Everything's a queue. Yep.
When you're doing the bind step, is that binding it to a location that your process on the machine, or is it binding it to like, say an IP address that other machine?
So it depends. You might bind a socket to a file, which would be like a location on your machine, or an IP and a port, which would be designated by your network and then handled by your network. But it would like listen to, you can even just listen to all incoming connections on port 80 or something like that, which is what a web server would do.
So you create the socket inside of the program?
Sorry?
You create the socket inside of an individual program?
Yeah. Yeah, so we'll have an example. So first you create a socket, and it, unsurprisingly, hopefully returns us a file descriptor, and then we can do whatever we want with it. In terms of a socket, you have to do a few extra steps. Yep.
So you said that like you can use it as a file, or you can make this socket a file, so you like can communicate with your own machine.
Yep.
Would this be used for that at all, like in actual software?
Yeah. So making a socket a file would be used in individual software, because essentially it sets up a pipe, but they don't have to be related. So all you need to know is the location of something, and then you can actually connect to it and communicate with it. So if anyone has used Docker, which is anyone using the dev container, it sets up a socket to communicate. So Docker actually uses a socket to communicate on your local machine. So anytime you run a client, talks to that, and it sets it up because it knows the location to that Docker socket. And yeah, we'll see an example of this too. Okay, and yeah, so the last step is to connect, the accept system call, and that will return whenever there's a new connection. So you call this multiple times on a socket, and each time accept returns, it returns you a new file descriptor that represents that connection, so between you and the client. So if you're the server, you'd call accept multiple times. Each time it returns means you have a new connection, and then it's a file descriptor, so I can just read and write to it, as we have been doing all along. So that's the server. It's a bit more involved. Client's a lot easier. So if you're the client, one socket is also one connection. So if you're the client, you create a socket using the same socket system call, so they start off the same way, where they essentially agree on a protocol. And then after that, the step for the client is simple, it's just connect. So I'm connecting to some location, and that would be whatever the location is set by bind in the server. So if I'm the client, I have to connect to whatever that address is. So if it's a file, I have to give it the path. If it's an IP, I have to give it that IP and port to be able to connect to it. And then connect would return, again, a file descriptor whenever it has successfully made that connection. And then I don't really care. I can read and write bytes to that file descriptor, and it would actually use a network connection if it's, an IP port, or actually use the kernel if it's just a local file. So, like I said, the socket system call sets the protocol and type of socket. So there's 3 arguments here. Basically, the last protocol one isn't actually used. People just use that term for other things. Typically, people just say the type is the protocol, but So domain's like a general protocol. So there's 3 main options you'll see here. So Unix is for local communication, which is on the same physical machine, which it will just look like a file, and that's how it communicates. And then there's 2 options. There's IP or INET, which is IPv4, which is just the normal number that most people use. And then there is IPv6, because we've ran out of IP addresses. If you do the math on that, that is what, 2 to the power of 32. That is not enough for all the devices in the world. So there's IPv6, which is essentially a 64-bit IP address. So type is like more what people say is like the protocol, and there's basically 2 options for type. There's stream and datagram sockets. Has anyone ever heard of like TCP and UDP before? So we got a few networking people that I expected, thankfully. Okay, a few. So these are closely related to TCP and UDP. So stream sockets, the underlying thing stream sockets represents is just TCP. And with that, it gives you a few niceties. This is basically the default option, which gives you what you expect. So all the data sent by the client is received in the same order on the server, which seems like a no duh, but as some networking people might argue, that is actually very difficult and something that is not a given once you're dealing with networking. So this also forms a persistent connection between the client and server. So if one of them disconnects, someone unplugs a cable, Wi-Fi goes out, whatever, one will know the other has gone offline because the connection will be broken. And essentially, you'd get an error from any system calls with that file descriptor if that connection is now broken. So this is reliable, but may be slow because, as you might figure out in a networking course, doing this is actually quite difficult. So the other option is datagram, which uses UDP, which you might have also heard before. And that just sends a message between the client and server. It's not persistent whatsoever, so the client doesn't know it's connected to, the server doesn't know how many clients are currently connected to it. It just receives some information, sends out some information. It has no way of knowing anything got received. It has no idea of knowing if that client is now offline. Nothing at all. It's really fast. but those messages aren't guaranteed to be in any particular order, and they're also not guaranteed to make it to the recipient, and you will not know if it has been dropped or not. So typically, people will use this because it's faster, it's simpler, and for some applications, you might not care. So if by the time you detect an error happens, that data is already old, then perhaps you don't care and you wouldn't bother resending it anyway, so why even bother having TCP? So an example of this would be like a real-time game or something like that. If you press a button and you send some packets, well, if you disconnect in the middle of it, it doesn't matter. You're not going to try and reconnect and resend that because it's already happened. Everyone else has already seen what's happened. So there's no point trying to introduce all that overhead with it. Might use it for video streaming, might not, depends how much you care about the stream. Some video streaming does use TCP though. So the bind system call. So that was the step 2 for the server. So it takes as the first argument the socket, which is that file descriptor that's returned from the socket system call, and then it wants an address. And because it's C, you give it a pointer and you say how big that pointer is because it's C and it can't really tell. So there's basically that struct socket addr, and there are 3 versions, one for each location. So there's socket UN for the Unix one. Why they shortened it from Unix to just UN, I don't know. But that's what you use to specify a location for a Unix file or a Unix socket. And it's just a path on your machine, so it just looks like any other file. It's just a little bit more special. And then there is UN. Again, I don't know why they shortened it from INET to just IN. Don't ask me why, and that's specifying an IPv4 address, so like 8.8.8, which, fun fact, that's a DNS server. If you're doing networking, you'll figure out what a DNS server is. Basically changes those numbers to something you can type like google.com or something like that. And then finally, there's socket adder in 6 for an IPv6 address. And the format's a little bit different, but it's essentially just a 64-bit address instead of a 32-bit address. So next step is after we have bound to an address, we have to tell the kernel how big of a connection queue we want. And it just takes a socket as the argument and then an int for the backlog that just says essentially how big that queue wants to be. And that's however many connections kind of queue up before they just get dropped from the machine before I can actually accept them. So the kernel manages this, yep.
So for the queue, I would assume it's like new incoming connections that would get cut off?
Yeah. Yeah, so it'd be new incoming connections that get cut off, and this is for things that you haven't accepted yet. So as soon as I accept, it creates a connection and then is removed from this queue and you don't have to worry about it. But this would be like if 10 million people try and connect while you're trying to accept some connections, instead of overloading your machine, it'll just start dropping them and say, nope, server's not available anymore, sorry. Yeah.
Is there an interface to find out if you've dropped any incoming connections?
So the question is there an interface to tell if you have dropped any incoming connections? And I'm actually not sure. I imagine so, but I'd have to double check. Yeah, so basically with this, all the time you'll just give the argument 0 to say accept the default argument, let the kernel worry about it. Kernel developers are pretty smart, so we can trust them. Okay, so the last one is restrict finally, step 4 of the server. So that is accept, takes a socket as the first argument, and then has an address, which is optional. So again, socket, still the file descriptor returned from the first socket system call, and the address and address length again are the same as the bind call, and that's what you would connect to, but it's just kind of like an optional thing, especially if you've already bound to something before and it's like a persistent thing. So you can set them both to null if you want to ignore them. And for stream sockets or TCP sockets, you've already set the address. It's always the same, so you don't have to worry about it. So after this, after accept returns, like I said before, it's a new file descriptor, and we can read and write as usual. Okay, the next one is for the client. So the connect system call looks an awful lot like bind, except it's on the client, and then connect will actually return you a file descriptor with that connection. So again, first argument, that socket file descriptor that's returned from socket, and then you give it the address you want to connect to, and that's the exact same thing as the bind, and they would have to match in the client and server in order to actually make a connection. So if this call succeeds, the only difference is that socket file descriptor is just used as a normal file descriptor. You can read and write to it whatever you want. All right, so let's see this example. So we will create it's not really a web server, so we'll just create a kind of server that sends hello there to every client and then just connects. So whenever someone connects to it, it just sends a message and then says, yeah, okay, bye, closes it, and closes the connection. So it is in your examples directory, and let's just see it and explore, and we essentially will play with this the rest of the lecture or do any fun questions. So here is my server code. So in main, I'm registering some signals, and we'll see why I'm doing that, because essentially this program will be an infinite loop, and I create some resources, so I need a way to clean them up. And I would clean them up in my signal handler and use that to exit my program. So we learn signals for a reason, because they actually come in handy when we have things like processes like this that essentially don't die until you tell them to die. So here we use that socket system call. We say we want a Unix socket, which will just be represented as a file on our machine. And we'll say we want a stream socket because we want things in order, because that makes the most sense to us. And then this protocol argument just isn't really used. Of course, we would check for errors, see if it returns -1, which means it said error no and and so there's this error no exit function. So next step is to set the socket address. So this is a Unix socket, and all it has is one field it has a field called Sun Family, which has to be the same thing, which has to just be that same AF value. It's just a macro, so it's just some type of number. So it actually knows what this structure represents. So the only other field it has is the sun path field, which is just an array of strings, and that's where that path goes. So we would use a string copy and just copy that path, and for the path, we set it as we're just going to say it's example.sock. So we're going to create a file called example.sock, which looks like a regular file, but it actually represents a Unix socket. So after we create this socket adder struct, we will bind, and we just bind using the file descriptor returned from socket, give it the address of that field, or address of that struct, and tell it how big that struct is, because it's C, and of course we have to. Again, check for errors, and then we'll do that listen system call. 0 is a default Q argument, so we just kind of have to call it. And we'll just check for an error. And then this is the meat of our server. So this is what pretty much every web server, if you tear it down enough, this is what they all look like. So it's just while true, so while an infinite loop, except. And except will accept an incoming connection. So if 9 people connect to this loop will execute 9 times. There'll be 9 accept calls, so we actually get a new file descriptor for all of them. So let's see what happens in one iteration of the loop. So we accept. If this returns, it will give us a file descriptor representing the connection. And accept is like a normal blocking system call, so it won't return until there's an actual connection, which is why we do, So it won't return until there's an actual connection, which again, might be a good reason to use threads for this and kernel threads, so we don't block everything. But for this, we don't even use threads, but a real web server would. So we accept, after it returns from accept, we have a connection. So we just create a message, get the length of the message, and just do our write system call to that connection file descriptor. So we're just writing hello world there, that's it. And then we, of course, check for errors, and then we close the file descriptor because it's like any old file descriptor. So that's what happens every time through the loop. So I can only handle one connection at a time the way this is written because I didn't make any threads, nothing's running in different processes or anything like that. But in a real web server, after you would have essentially one thread that's just doing accept over and over again, and it would create a new thread to handle that connection and go ahead and go do that. So that's more what a real web server would do, but this one's really, really fast. So it just sends a message and closes. And then, and then in our client, well, it's pretty much the same thing as the server. So it creates that socket, checks for error. Like I literally copy and pasted this. It's the same socket address, goes to that same path, which would be example.sock, and then tries to connect instead of do bind or anything. And then after connect, it can use that file descriptor. So here, we just create a big old buffer that's the size of a page, do a read system call, and we just do it in a while loop just to read all the data we can, but we know that it's only going to read one line and then return 0, indicating that it's closed. We'll check for an error, and then we'll just print off whatever string we get, and then close the file descriptor. So let's see this. So in here, if I run build.server, looks like it's not doing anything because it's at that accept system call over and over and over again. Well, if I go to my other shell here, I'll see once I started it, there's this example.sock, and it just looks like a file. And since we did the inode lecture yesterday, we can actually check it out because, oddly enough, it is also an inode. So the socket's represented by an inode, but it has 0 blocks. It doesn't take up any space on the device. It just kind of looks like a file, but it isn't really a file. But it does get an inode number because it has a name, so it needs a way to refer to it. But if you connect to it, the kernel will do stuff. Yep.
So if, I assume .sock is like it was the same thing, but it would work the same if you had any other file name?
Yeah. So .sock is just a convention, but I could have called it whatever I want. All right. Any other questions about that? Okay. Well, now if I'm the client, I can run the client and I see I received hello world. So nothing in there had, or nothing in that client program had hello world. It comes from the server. So whenever I run it, connects to the socket, and then the server sends it data, reads the data, and then it closes itself. So that happens no matter how many times I run it, and it just receives all the time because the server is just there in that big old loop. Now, if I want to stop the server, well, I can hit Control-C because I registered my signals, and we'll see why we did that. So let's go look at our signal. So we registered a signal to call this handle signal function. Handle signal just calls close socket just because I wanted to be really intentional with what the name was. And close socket is what cleans it up. So it closes the file descriptor representing the socket, and then it does this unlink system call. And remember, unlink just removes that name. So whenever I don't have that server, I don't want that file to be on my system. So it does this unlink system call while it's exiting just to clean up any resources they have. If I didn't have a signal handler or anything, that example.sock file would still exist in that directory, but it wouldn't have anything actually listen to it. It would just be like a dead file, so there's no point. You should actually probably clean it up. So now the server is not running, so that example.sock is not there. So now if I go to my client, oh, well, now my connect system call gives an error because I can't connect to that socket because Well, two things. That path doesn't exist anymore, and also there is no program listing on it. Yep.
Does that raise error? Like, did that set error no, or did it just exit the program?
So this set error no, but let's see, client. So yeah, so I got an error from my connect. So connect returned -1, and then it went to this error no exit because yeah, it sets error no. All error no exit does is do p error with whatever I gave it, which was just connect. And then, yeah, so it prints that message from the error no. So it would have the error no such file or directory. Yep.
What would happen if there's a client connected to the server and then you terminate the server while the client's still connected? Would this client receive like a signal?
Yeah, so the question's what would happen if I killed the server as the client was doing something, if it went back and forth a few more times? And the answer to that is because it's a stream connection, you wouldn't get a signal when it died, but you would get an error whenever you tried to read and write to it again. So whatever the next thing you're going to try and read and write, you get an error from that system call. And then you can go ahead and handle it. All right, any other questions? And this is like the kernel interface, so the only difference between this and your web browser or your web server is that it just listens to IP addresses, but everything is the same. So this is a server. Chrome's going to use the socket interface because that's the kernel interface for networking, and you can't do anything about it. So everything will use this. Yep.
If we're connecting to a network,
Yep.
do we have to do any more work to set up like the TCP or networking?
Yeah, so the question is, if this is actually going to the network, do I have to do any more work? And the answer to that is no. So the only thing you have to do different if you want to connect on a network is you just use socket adder for IP or INET, whatever they call it, or IPv6. That's it. That's the only changes you have to make. Otherwise, it's exactly the same. Yeah.
So then if I started the server on, whatever address, like my IP/0,
Yeah.
would other computers connected to the same like Wi-Fi be able to see it, or?
Yeah, so the question is, if I just start a server that listens on anything, can other people connect to it? And then the answer to that is, depends who's running the network. So the Toronto network, it will not let you do that. So you won't be able to just host a web server and it communicates with everything. You have to ask nicely because all the networking people can block ports between machines because they're in charge of getting data from A to B, so they can block everything if they want. So yeah, it depends on your network setting. If you're at home on the same local network, you can do that all you want. You can connect to it because probably there's no restrictions. But yeah, all the other stuff of making sure the number you put in actually connects to a machine, that's all a networking problem, which is another course. Yeah.
Just going back a bit to the type of, what do we call, like sockets?
Yep.
Like the TCP and the UDP.
Yep.
What are some examples of like when you would use one as opposed to the other?
So basically you would use stream sockets whenever you want to actually know someone has disconnected, and it's really important to get the messages in order, and you really want to be reliable. UDP doesn't have any of that. It just sends a message and it's like hopes for the best. So generally, if you want something to be persistent in order and everything, you just use TCP. Otherwise, you use UDP if you don't really care about the data. And then there's like in-between things. So sometimes people build their own things on top of UDP to like, hey, you should send me a message if you're still alive and like that. But eventually you add so much stuff on top of it, it becomes TCP, but crappier. So
What's like an example of like, is there like a concrete example, or is it?
So concrete examples, so everyone's used SSH probably. So SSH uses TCP. So that's an example because everything you type, you get in order, you send it in order. You probably want everything in order. Example of UDP, probably more like if you were actually listening to this, like live streaming something, a lot of them use UDP because if you lose a connection, Well, it's live anyway, so whenever you catch up, you just get the latest thing and you missed that minute or whatever you were disconnected for. So it wouldn't even bother trying to retry and do that. Yep.
Which one would database connections fall under?
So database connections typically are TCP. So they want to be persistent in order. You send a message, you get something back. You probably want to know when they die or not. But yeah, most things generally now use TCP. Generally, the only things that use UDP are like games, like video streaming. Sometimes some video streaming uses TCP, but that's like the two main ones. All right, any other questions? Because this isn't really anything new except a few new system calls and an address, but this is just another form of IPC and connecting between different machines. So there's a few different ones. So instead of read-write, there's also like specialized socket ones called send and receive, but they're basically the same thing, except they have a few more things if you actually care about networking. So some of them, examples are like message OOB or send and receive out of band. I don't specifically know what that means, but it probably means something to networking people. There's a peak system call that essentially won't increment that position. So it's like I want to just check what's at the beginning of this packet or beginning of whatever I got sent during the connection. And I don't want to advance the read. I just want to look at it and then maybe forward it on to something else. So that's peak. And then the last one is don't route, which is a weird thing because typically whenever you connect, there needs to be like a connection between two servers. That's mostly for if you are like super in the weeds of networking and you're implementing your own router or you're doing some insane network debugging. These are things you'll probably never see. Except for message peak, there's no way you'll ever probably use these or need to know these. And then there's also send to and receive from, which takes an additional address. Like if it is a UDP socket, you don't have a persistent connection, so you don't need to connect. So you can just send to, receive from, and those take the address as one of the arguments. So you can just send directly to that address or receive directly from that address. And those are completely ignored for stream sockets because you already have a connection. They're only for the datagram sockets. So that's pretty much it for sockets. They're just IPC, but they're across machines. And the basics are they just require an address. So if they're local, it just looks like a file. If it's on the internet, it probably has an IP address, which just looks like a number. And if you wanted to, you know enough that if you wanted to connect to any server, you can use that, put in the IP address, and do a read system call and just see what you get. So you could use that for any server as long as you figure out the IP address. Just connect to it, do a read, see what you get because you'll probably get something. So there's two types of sockets. There's stream and datagram. Stream are the ones that are always in order. Persistent connection, you know whether or not that connection is broken. Datagram is just like throwing messages out into the wind. You don't know if they'll get there, but you'll hope they'll get there. They might not be in any particular order, and that's just how they work. And then if you're a server, all you have to do is bind to an address, say you're listening to it, and accept some incoming connections. If you're a client, all you need to do is connect to an address. Then on both sides, you just have a file descriptor, same read and write system calls we all know and love. So any other questions about this or the lab or anything at all? Again, like I said, we're like in the chill third of the course, so we're cruising. All the hard stuff's already done, ish. All right, so just remember, pulling for you.